working with wind power modeling for many years. Anca is an associate professor at the Wind Energy Department. She has received a PhD degree in modeling and control engineering from DTU, and her research interest is wind power integration and control, including wind power plant modeling and control and ancillary services capabilities, and provision and coordination between different wind power plants. Anca, the screen is yours.
Thank you, Kaushik. So now is the last presentation today after a long day. So I hope that you are not sleepy. As Kaushik has mentioned, I will talk about wind power capabilities to provide ancillary services. And for sure, you have heard the terminology, the term ancillary services for several times during this workshop. I will maybe repeat some of the things you have already heard. The presentation is done in such a way that is from the wind turbine in wind power plant perspective. How is the interaction of the wind turbines, particularly with the power system? So let me see if I have. Yes, so I will go through quickly through definition and types of ancillary services. Then I will talk a bit about typical wind power plant architecture. And then I will present our research results regarding ancillary services we have achieved through a lot of research projects during the years. So yeah, active and reactive power control, voltage, frequency control, and also our results regarding enhanced ancillary services such fast frequency control, also referred as temporary frequency control, capability about power oscillation damping, and Blackstart capability from wind turbines. So why ancillary services? Yeah, you have heard that several times. To summarize is the fact that ancillary services have as goal to ensure that the power system operates securely and that there is reliable, high quality power supply to the customer. So yes, ancillary services are vital for the security and stability of the power system, which, as Damien and also other presenters, they have highlighted yesterday and today, that the power system is getting more and more complex and vulnerable and require appropriate operational rules and control systems to ensure their operational security and stability. There are several definitions. For example, according to a Sigre report, the definition of ancillary services can differ significantly based on who is using the terminology. For example, some of them emphasize the importance of ancillary services for power systems, security, and reliability. Others mention the use of ancillary services to support electricity transfer from generation to load and to maintain the power quality. Some definitions also limit the contribution of ancillary services to the transmission network, while others include distribution purposes as well. One should also remark that some of the services required to ensure the power system stability are embedded in conventional power plants using directly connected synchronous generators. And this means that as it is planned in the future to displace more and more conventional power plants by renewables, it is also need to define new enhanced ancillary services products to ensure stability in the power systems with large penetration of RES. And this is an ongoing process. So despite all these differences in formal definitions, the focus on insurance of system security and reliability is considered the most widely accepted among transmission system operators. One should also be aware that there is a distinction between system and ancillary services. So the frequency and voltage control services are called system services because they are defined by the power system to all the users, while ancillary services are ancillary to the production or consumption of energy. They are provided by some components of the system, such generators, controllable loads, network devices, and contribute to these system services by acting on the frequency of the system or voltage at the point where they are connected in the system. So I will give a bit of historical process of ancillary services. So the most commonly generally discussed accepted ancillary services belongs to the group known as active power reserves, and they are by nature related to the power balancing in the system. And their goal is to cope with unexpected imbalances, which typically occur due to errors like forecasting power demands and production, unexpected plant shutdowns, trippings, or contingencies in the grid. And for example, in the SIGRE report, we find definition classification of ancillary services based on the sequence the ancillary services are expected to operate. So we have primary frequency control, secondary control, tertiary, and voltage control, and Blackstart services. While in Denmark, Energinet has classified ancillary services into frequency control reserves, secondary reserves, manual reserves, regulating power, and the group of other properties required to maintain power system stability. And these properties include short circuit power, continuous voltage controls, voltage support during faults, and inertia. In these two classifications, so primary, secondary, tertiary classes are very uniform, and the voltage control service in the SIGRE classification is similar to the continuous voltage control service in Energinet strategy. The main difference between these are that the SIGRE includes Blackstart capabilities, while Energinet includes short circuit power, voltage during support during faults, and inertia. And yes, you have seen this maybe before. I'll go very fast. So the European Transmission System Operators report, the classifications is based on the process that the reserve is support. So we have the frequency containment reserve that are operational reserves activated to contain system frequency after the occurrence of the imbalance. Then we have the frequency restoration reserves, which restore system frequency to nominal frequency. And then replacement reserve, that are the reserves that are used to restore and use the required level of frequency restoration reserves to be prepared for additional system imbalances. I want to mention about this reservices project, which have studied the benefits of providing reserves from renewables in different types of power systems. For example, island system, as the case of Ireland, or the Iberic Peninsula, so the end of line power system, and the large North European. And the conclusion based on this project is that the results clearly show that the benefits of getting services from renewables increase when with an increased penetration of renewables. As I mentioned before, the large penetration of RES has also created requirements, and it will continue to generate requirements for new ancillary services products. So as new ancillary services product, we have the fast frequency response and inertia response, synchronizing power and power system oscillation damping, and of course, Blackstart capability. Sorry. A bit about the grid code requirements. So the technical capabilities of wind power plants to provide these ancillary services are commonly required in grid code. So they require an operational behavior from wind farms more similar to the conventional generation capacity, and ask wind power plants to have more responsibility, behave as active components in the power system. The very first grid code dedicated to wind power plants was introduced actually in Denmark in 2000 in order to prepare the first large offshore wind power plant connected directly to the transmission system. The only required ancillary services at that time was a remotely controllable maximum power set point. And a special power control in the case of frequency transient was also mentioned as a possibility to be included in the connection agreement, but it wasn't a general requirement. Still, at the time, the first large offshore wind power plant in Ons Reef was capable of providing frequency support. In the later grid codes, there have been added more requirements, frequency control, reactive power, and voltage control capabilities, as we all know today. The new common European NTSOE network code also includes enhanced ancillary services such as power oscillation damping and synthetic inertia. Looking at the Danish grid codes, so the main attention in this grid requirement is drawn to the fault right-through capability and the power control capability. Fault right-through capability addresses primarily the individual wind turbine controller rather than the wind farm controller, in such a way that the wind turbine is able to remain grid connected during grid faults. And with respect to power control capabilities, wind power plants have to participate in active power frequency control as well as reactive power and voltage control. And the Danish TSO involves different types of power control. You may know about this balance control, where the wind farm production can be adjusted downwards or upwards in steps at constant levels. Then we have the delta control, whereby the wind farm is ordered to operate with a certain constant reserve capacity in relation to its momentary possible power production capacity. We have also the power gradient limiter, shows how fast the wind farm production can be adjusted upwards or downwards. The automatic frequency control, whereby the wind farm must be able to produce more or less active power in order to compensate for possible deviant behavior in the frequency, measuring the wind farm point of common coupling. And then we have, of course, the reactive power control. So wind farm is required to produce or absorb active power. And the automatic voltage control, where it's ordered to produce or absorb an amount of reaction power in order to compensate for the voltage in a point of common coupling. So going back to wind farms, traditionally the main aim of wind turbine control was to ensure that the wind turbine was able to produce energy at the lowest possible cost. And this means that the control aimed for the maximum possible power production and to meanwhile to reduce the structural loads on the mechanical components and thus to make possible to keep the reduced cost of the mechanical components. However, as we all know, wind power penetration into the power system has increased drastically. So the power system has become more dependent on the wind power production, and there is continuous serious concern for power system operators, and this leads to the situation that today wind farms should behave as active controllable components supporting the grid. So they are not just their goal is to produce power, they also have to support the system in the similar way as conventional power plants do. So the aim is here to improve the integration of wind turbines in the power system in order to secure quality, stability, and reliability, and to reduce the required grid cost. All these are implemented in the wind farm controller, and of course the wind farm controller should interact with the wind turbines controller to provide the grid support, and this should be done in such a way that the individual wind turbines maintain their ability to maximize power production and limit mechanical loads and lifetime consumption. You may have seen that there is not a very consistent use of terminology wind farm, wind power plants, when we use what, and we try to define better the terminologies, and we decided to say that, okay, wind power plants are wind farms with power plant characteristics supporting the grid. So they are controllable components in the power systems, while in old days we had just wind farms producing power. Over the years, we have had several research projects at Wind and DataU Wind, and we have developed a database of dynamic models and control strategies for different types of wind turbines, wind farm technologies, including both wind farm controllers, individual wind turbines controller, and dynamics of the wind turbines themselves. The models typically working the time frame from milliseconds to minutes have been applied to simulate the behavior of wind farm controller whenever the wind farm is connected to large and strong grids, but also to small and isolated grids. We have used different modeling approaches, individual and aggregated, and of course individual modeling in cases where, for small wind farms, where we look at the interplay between wind turbines inside of a wind farm and having a good overview on the dispatch references from wind farm controller to each individual wind turbine, where aggregated modeling, and maybe most of you are using this, is used for power system studies, where the focus is on the impact of the entire farm on the power system. Yeah, and here, we use the entire wind farm represented by an equivalent lumped wind turbine with a pre-scale power capacity. Here is a typical wind power plant configuration. It consists of wind power plant, several wind turbines connected to the main grid at the point of common coupling through a transformer. We have a wind power plant controller, and we have communication and measurement devices for voltage, current, grid for frequency and power at the point of common coupling. Wind power plants can support the power system, and this is typically done by communication and control. The power plant level by wind power plant controller, and as you can see, the wind power plant controller communicates back and forth with every individual wind turbine controller through a set of signals in order to control the power production from the whole wind farm and to provide support if required. Inside the before this, we can see that the wind power plant controller is getting external power set points and comments from via SCADA system, and this uses also a wind power forecast algorithm to estimate future available wind power. Inside the wind power plant controller, there is a grid monitoring block which delivers information about the grid condition, grid frequency, gradient estimation, active and reactive power calculations based on voltage and current measurements. Then there is also a dispatch block which distributes the individual power set points to each wind turbine, and these set points are generated based on the measurements, set points from TISO, and also on the wind turbine conditions. If maybe one of the wind turbines is not running, so the wind farm controller is getting information about that before defining the references for the wind turbines. Then we have the so-called support services, which contains different technical control functionalities, as I show you: balance, delta, frequency, and voltage control. And there can also be a services allocation block, which makes possible to select, activate, or even combine sequentially or simultaneously multiple control functionalities with a specific weighting. This is a wind power plant control architecture, consists of a wind power plant control and wind turbine control level, and these two interact to each other through a set of signals, power set points, and status feedback signals in order to provide relevant grid support. And here the wind power plant controller is also getting information about the available power of the wind turbines. So as you can see here, the control functionalities of wind power plants to provide ancillary services are typically integrated in the wind power plant level. So we have here active power control, balance, delta, power reference, ramp rate control, frequency control, reactive power, and voltage control. And notice also that these control functions for active and reactive power are implemented in such a way that they can be active at the same time. And then, as I mentioned, we have these new ancillary services, temporary or fast frequency response, synchronizing power, and power system damping. And yeah, the wind power plant level behaves as a single central unit, prepares and sends further references to each individual turbine. And depending on the actual grid status, the system operator issues specific demands for the wind power plant, and it specifies which should be the production of the wind power plant at any time and in any conditions, namely either maximum production or curtail production according to different tasks, exactly as a conventional power plant. This is a more detailed look in the wind power plant control architecture with the control function block, main controller, and dispatch controller. And here we have the basic control features, and we have the enhanced control services. Notice that in this implementation, we have wind power plant controller has two concomitant control loops, one for active and one for reactive power. And we have the dispatch distributing individual references to each turbine. We have this service allocation block I have mentioned, which makes possible to select, activate, or even combine different functionalities with a specific weighting. And of course, there is estimation of the available power for wind turbines, and this information is received by the dispatch control. Yeah, this is even a more detailed look in the controller. So we have this active power control loop with a subordinated frequency control loop, and the similar ways for the reactive power. So now I will go showing you some of the results, simulation results we have achieved during the year. So we'll start with the active and reactive power control support, right? And we'll show how these functionalities, balance, delta, power gradient, and reactive power control looks like in a simulation of wind farm. As you can see here, we have 3 wind turbines, and the goal here to show how different control functionality can be activated consequently or in the same time. So we have production of wind power plants, 3 wind turbines, wind speed of 9 meters per second. So it's not big, not very big, not very low. What do we have here? It's the active power, and we have 3 signals. We have the available power. This is the blue one, so shows how much wind power can be produced if there are no actions, no curtailment. And then we have with red the actual active power, and you can see that based on the system operators giving different control actions, how the wind power plant reacts. So in the first graph, we say, okay, produce as much as you can. And so you can see that these two follow each other. Then the wind power plant is asked to run with a delta balance. It's starting running with this reserve, and then on top of this, we asked wind power plant to run with the balance control, and then back. And of course, we also have implemented the ramp limiter on this, so how fast the wind power should be changed. And this is repeated this again. And then if we take a look on sorry, it's nothing happening. I have problems with my internet again. Restart the program, or what should I do?
There should be an option of postpone, no?
It's, yeah, restart the program, close the program, and wait. I'm close. Yeah, sorry. Yeah. Restart the program. Yeah. What to do? It's restarting now. May I see? One moment, I am there. Okay, I have to go through. Oh. Yes, so We are back again.
But it's still the same. Yeah, now we can see.
Now it's changing.
Yeah.
I just wanted to show that. Let me have this one. While we do different changes in active power, so we also require, we can require the different demands from the wind power plant in respect with reactive power, and it can do it independently. Of course, this is modern wind turbine, DFIG, as far as I remember, but the same is also for type 4. Oh no. Yeah, I'm hanging again. I really don't know what's happening.
Maybe it's a full screen mode. Maybe then you can get out of full screen mode and continue. Not in the being in the presentation mode. Maybe it's too heavy, these figures.
Yes. It's so irritating. Restart again. Yeah, I will not put it in the slide mode. So starting again. Let me see. I'm going directly to the slide. Pop. Yes, so I will go further. Shall I show it? Yes. This is a next slide. So what we have here, I have shown the active power performance, and now we have wind voltage control, and here we had the transmission power system delivered by an EGINET, and we have extended with an offshore. I don't know if you can see, but I'm afraid that it will hang again if I'm doing this. We have extended the model we got from an EGINET with an offshore wind farm, and we're looking at voltage control capability and how type 3, type 4 wind farm can support an old wind farm with fault right through. So as you can see here, we have voltage, the point of connection of wind power plant, and its reactive power in two situations, with and without voltage control in the wind power plant. So notice that the voltage control is visible both during the fault and after the fault, and when the voltage control was not enabled, it's a blue curve here. The grid voltage oscillates and stabilizes at the higher voltage level, and this is due to the fact that some of the old-fashioned turbines, the Type 1 turbines, were disconnected, so there was a surplus of reactive power. While when we enable the voltage control inside the wind power plants, you can see that we can control nicely the voltage back to 1 per unit, while the wind power plants here, by the red, is able to absorb the reactive power existing initially in the system, and therefore able to control the voltage at 1 per unit. No, I'm sorry for this. I really don't know what's happening. No, No.
How many slides do you have, Anca?
I have, yeah, I'm on 18 and I have up to 32.
Okay,
So,
maybe you can send them to me and I can share if that would help.
yes. Okay, thank you. I will do that. And sorry for this. I can do that. Let me see. Restart. So I'm doing this. And yes, and I will you will share the screen, right? I have to find.
You are still sharing, Anca.
Yeah, but I'm trying to disconnect. Everything is hanging. You cannot kick me out, right? Now I'm disconnected.
I can. I think I'll try that now. Not to kick you out, but slide 18, you say. Is this the slide, Anca?
Let me see if I can see it. Yeah, these are the slides.
Yes. So should we continue from this slide or?
Okay. Let me see. Oh, sorry.
Yeah. No, it's me. But
do you share that? I cannot see it.
Can you not see my see in the Teams?
No. Do all the others can see it? I do not see it. I do not see the slides.
No. The screen is dark.
Pardon?
I also can't see it.
I do not see.
You cannot see the you cannot see the slides at all.
At all?
Yes, I can see it.
No.
Yeah, it's a black screen.
Yeah, for me as well.
Oh, then what about now?
Still?
I think Kaushik, you only shared the presentation, not your entire screen.
No, I did share the entire screen. Disconnected. I know someone is dreaming. But what about now?
I do not see anything.
Okay.
It's just black. Julia, she's writing something. Oh my God.
Still black screen.
Still black screen, yeah.
I think you can also convert the point file to PDF.
To PDF, yeah.
Yes. But then probably will not have those animations.
Doesn't matter. It's okay. It's okay. I'm very thankful that you helped me with that.
No worries. But, converting just so you know. Now I share. Can you see the screen now?
No.
What?
Then this time I will stop. Try to share only the application. How is it now?
No.
Have you made an Adobe?
Yeah, but still.
Okay. I'm also trying. Maybe I can show the Adobe. I don't know. It's amazing. Or I'm also trying. This means that yeah, the computer is tired.
No, but it cannot be both our computers are tired. But do you see anything now?
No. I'm trying to share my screen. Now I have.
I'll try once more, Anca. Then
okay.
you can.
Okay.
Is because I have another screen. Does it share anything now? Do you see anything?
I do not see anything.
Okay. So
no, but let me try to
this
share.
This is a Teams problem.
Let me try to share. Can you see my screen now?
Yes, I can see your screen.
Okay, this is
Okay, it's normal now.
It's what? It's Adobe.
No. Yes, it's normal. You can play it with the sliders.
Yeah, we take it from here. Sorry, guys. It's okay. So I have said this to you. So what? Here I will go very fast. The idea here was to show. We have 4 cases, and to show how type 3, type 4 wind farm with an voltage control equipment equipped with a voltage control can actually help an old-fashioned wind farm in nearby wind farm nearby with respect with voltage and going during forthright through. So in principle, you can see 4 cases here without voltage control in the type 3, type 4, and with and without reduction of power in the active stall wind farm. And the best case here is clearly the case B, where wind turbine is equipped with wind control, and you can see also here both in respect to the active and reactive power. If we go further, here we have had also an investigation done by our PhD student, finished last year, about voltage control, grid support during stress voltage conditions, and we have looked at different control strategies, reactive power droop and voltage control evaluated during stress voltage conditions, and the efficiency of these controls have been quantified through maximum power transfer capacity. And you can see that the maximum power transfer was improved to 1.5 compared with the other control strategies. Then I'm going quickly through this. I'll not go in details. It's just to show you. I don't know if you see my I don't know what it is. Anyway, here in the bottom, you can see how different types of wind farms reacted voltage drops. So we can see that fixed-speed wind turbines actually provide inertial response, supporting the frequency during the fault. So it reacts like a conventional power plants, while the other DFIG and PSMG, they do not react at all as expected, as they do not have, they are decoupled from the grid, and so they do not have inherently system inertia like fixed speed wind turbines, so they don't see any deviation if you do not equip them with a proper control. So here the idea is how we there are different ways to control the frequency. So you can have inertia control, droop control, combined control, and whatever. And this is an example of how does it look when we have different things in respect with nadir rated Rokov, and also depending on where you place the droop control inside at the wind farm level or the wind turbine level. And of course, you can see quickly here that the combined control in this situation gives the best performance. And this also very quickly, it's about short-term overproduction capability. So how it is seen, this fast frequency response capability depends actually on the initial pre-overproduction conditions of the turbine. Here we show how the wind turbine reacts when different steps in the active power requirement for them is expected, and this is done for different wind speeds. And what is crucial here is just that this capability depends on the wind speed, on the limits, the mechanical and electrical components in the wind turbines, and the control strategies. This is important for reliable frequency support. And you can see that the wind turbine reacts differently depending where. So below rated wind speed, higher wind speed, and so on. And it's below rated wind speed, the overproduction is followed by the recovery period. And this recovery period is larger when you have bigger overproduction. So this is interesting to have in mind when design this capability. Here is how does it look when we have more and more wind penetration in the system. And what I want to show here, we have tried to look at two cases. For example, this is also different for if you have 20% wind power penetration or 50% wind power penetration. And here we have how does it look. We had loss of largest unit out, and how does it look with and without this fast frequency response control. And of course, you can see that with fast frequency response, it's the performance is better. And we're looking at, in the case of 50% penetration, where we can show basic without wind turbines, with wind turbines, and then we try to put this fast frequency response control in each wind turbine. So first we had in the first one only, and it was red. Then we put it in the two wind power plants had this capability, and then they had three capabilities. And then the conclusion is that you can see that by just having more and more capabilities, so all the wind power plants have this capability suddenly in the same time, and this doesn't mean that the performance get better. So there is a need for coordination between wind power plants. We have to do it in a smart way. So this is actually also something similar Damian showed yesterday. So the case where we have in 3 wind farms is not necessarily better than when we have only 2 wind power plants. Yes, and then yeah, it was about this impact of communication of fast frequency support. Of course, that depends. This capability highly depends on the underlying communication infrastructure that allows an exchange of information between wind power plants and control schemes. And then we were also looking at the wind power oscillation damping from the capability for example, also for 50% wind power penetration scenarios. And we have looked at different scenarios, configurations here for POD, different inputs, output signal pairs, different modulating either active or reactive power. And we have assumed that all the POD in all the wind power plants had the same parameters, control parameters, and this is a strong assumption, but maybe this is not the case in reality. But anyway, and this is a similar situation when you have the POD activated in only 1 wind power plant and it works fine, but if you are not careful how you are doing this POD and you want to put them in all the wind power plants in the same time and you do not do coordination, this doesn't mean that you will have better results. You can make it worse. So coordination, it's a key word. Then I have just few slides about Blackstart capabilities, approaches. As you may know, there are two Blackstart plans approaches. So one is the top-down. So we start from neighboring interconnected systems. As Bent also mentioned this morning, and in the case of offshore wind power plant, this means that you use the onshore grid to energize the offshore wind power plant via HVDC link. While on the bottom up, this is done by restarting your own generators, and yeah, it makes locally. So I will show you this in the next slide. How is this done? Yeah, so here we have different perspectives. We have TSO perspective, which is likes that early participation in the power system restoration, right? And thus reduce restoration time. So TSO likes that wind power plants have these capabilities because reduce significantly the intensity and duration, the overall impact on the blackout events. On the other side, the wind power operator perspective is that no, it's not waiting for end of network restrictions, and this can be control island in operation to ensure the continuity of power supply. And then here I can show you how is this. It's called when it is button up. It's called. It's well known more as a green start, and this is the wind power operator perspective, right? Where the wind power plant equipped with a grid forming capability means that the wind turbines do not have to wait for completion of the network restriction, but can also do control islanded operation to ensure continuity of the power supply. And here are different steps. As you can see, we have self-start of the turbine using internal backup power supplied for initial energization of the components. So start produce power from wind without depending on external power supply. And then its next step is self-sustain is called, where the rotor is oriented to the wind direction, and wind turbine can start rotating and producing energy to sustain itself. Then we have parallel operation, where once wind turbines, they can sustain themselves. So the next step is synchronization, parallel synchronization startup of multiple wind turbines, and then we have offshore grid forming, consisting of coordinated parallel operation of multiple wind power plants in a cluster to form the isolated offshore. And at the end, it's this so-called cluster islanded operation, which is done when the whole offshore cluster is operating, so it's connected to the main onshore grid. And for sure, yeah, Nikos could tell you a lot about this, as he has had some PhD students working on that. So some reflections. Yes, wind power plants can deliver basic ancillary services, and they can replace conventional power plants, different control functionalities, and they can also provide enhanced ancillary services. And as I have shown, in my opinion, coordination of wind power plants to provide ancillary services is quite important, as and this is a major challenge for high share of renewables in the future. So thank you. I am over time, and sorry for all these problems.
Thank you, Anca. No, we owe you some extra time, and I already see some hands rising, and it's Mustafa. Please go ahead, Mustafa.
Hello again. Do you have my voice now?
Yes.
Yes. Okay. Thank you, Anca, for this presentation. I have a couple of questions on the ancillary services of the wind power plants. Actually, it's kind of comment rather than a question, but I would like to have your opinion on it. There are, like, when the wind turbines are participating in inertial control or frequency regulations, they will go through the stage of re-acceleration or recovery stage, when the rotor speed will try to go to the maximum power point tracking. However, in a lot of literature, almost all of them actually, this recovery stage takes 2 minutes. But the problem in reality is that the wind speed is not constant, which is different from academia. How we can put these techniques into reality? Because if recovery stage takes minutes, it's an unstable stage for wind turbines. Maybe the wind will drop, and again we will have another unbalance to the wind turbine due to the swing equation.
Yes, it is a quite complex question. This recovery, as you can see here, is mainly at low wind speeds and also medium wind speeds, and it is right that the longer recovery period can actually have a big impact on the power system stability as well. So it's quite complex.
But if I may add, I don't think that recovery takes minutes.
Here we have seconds.
Yes,
okay.
it takes few seconds, and in that, wind speed can be assumed quite stable at that point.
Yes, yeah, even in few seconds, I mean, in simulations, we consider constant wind speed, but even in few seconds, wind could drop from 11 meters per second to 10. That would be another.
If you are looking for a large wind farm, for the all wind turbines, it would not probably drop from 11 to 10 within a few seconds. So it's in that way, it's quite stable. In a large wind farm, you do not see that fast ramp, and like even that fast ramp gust for a single wind turbine is probable, not for wind farm. So I don't think it would be for minutes. You would see that kind of difference.
Yes, for sure. You also have to remember that there is a smoothing power at the wind power level as well. So what do you see at individual wind turbine is not that you are seeing at the wind power plant level. So
right. Yes. If I made my point clear, because when during the recovery stage, let's say the wind will drop from 11 to 10.5, not even 10, because the electrical power output of wind turbine is below the mechanical power. That means the rotor is going to accelerate. However, when the wind drops, there is a possibility that electric power output will go beyond or above the mechanical input. That means the rotor will start to decelerate again. So it will go to the rotor stall point.
Yes.
So
depends on how you implement your control. We have of course a limit on how low the rotational speed can go down, because otherwise the turbine will stall. So this is should be implemented in your control. I mean, now I'm saying it from the wind turbine's perspective to protect the wind turbine.
Right.
Exactly.
Yeah, thank you
I think that is the major concern, if I may also. Maybe I was too fast in answering before, but I think wind turbine is the major concern here, and probably that's also your question. And we haven't seen, as per my knowledge, many wind turbine providing synthetic inertia, because that impacts the health of the wind turbine. If somebody is providing, probably they would have some other kind of system there, be it battery or a supercapacitor or something connected in their wind turbine to provide those services.
Yeah. Yes. I mean, we have had this one together with Vestas, and it was clear that in order to protect the wind turbine, we had to have this limitation, how much down the rotational speed can go down.
Thank you, Anca. Then I see. Thank you, Mustafa, for that question.
Thank you so much. Yeah.
And then I see Julia raising her hand. Julia, please go ahead.
Yeah, hi again. Anca, I wanted to ask where you were showing Blackstart from wind turbines. Is there some initial source of energy used to power auxiliaries? You might have mentioned it, I just missed it.
One more time, I didn't catch it.
If there is some source to power up auxiliaries in the very beginning for a wind turbine. If there is a battery or something else that just.
I'm not sure. You mean this is cell start? Depends. Yeah. Depends. It can be. Depends on the strategy you use. But I'm pretty sure that this detail you can find in this article. I don't remember actually that. During the cell start, if they have any help there just when they're starting, or they.
But that figure shows there is a UPS there to provide that.
Okay, we cannot see clearly.
If you can zoom somehow.
Yeah, it is an UPC, yes. So it is a small help.
Small help. Yeah. That's the reason why I asked. I've seen they tested in Scotland they tested some wind turbines for Blackstart, and they use a small diesel there. So that's yeah.
And I think that is also the major concern for offshore wind farm, because putting the diesel, one thing is that you need to refuel the diesel and whatnot, but also it has challenges in terms of safety and security. So that also increases the insurance cost. So Anubhav was also looking into that in his PhD, that how to get rid of diesel through battery storage or something. I think that's a major challenge there. That in order to provide a Blackstart, how can you get rid of diesel?
And it is still a lot of research going on that. It's not. Yes.
And I thank you for the answer, Anca, again. And then I see Yuan. Yuan, would you like to introduce yourself before you ask the question?
Okay. Hello, Anca. My name is Yuan from the University of Warwick, and I'm very interested in the power oscillation damping from the wind farm. As we know that the wind farm can use the POD signal from the onshore power grid to damp the oscillation in the power system. What's your suggestion on the POD signals? Because when the wind power plant receive the POD signal, they should send the signal to each wind turbine. So how the wind power plant locate the POD signals?
Locate. I mean, you mean distribute or?
Yeah, distribute. Yeah.
Yes. I really don't remember exactly how was it implemented in this simulation, but we have observed that it was quite sensitive. The results were quite sensitive to which input-output signal pairs we were investigated, current or power. How we did it here, I think, if I remember it right, it was a kind of proportional dispatchment. But of course, a more complex dispatch control strategy can be implemented. There are some few years ago I have worked on that. It was also quite relevant on you had local measurements or what's his name of or far away measurements comparing with your decisions. So this was also quite important to take into account. But regarding the dispatchment, I think that at this time it was done in the proportional way.
Yeah, okay. What I mean is that whether the POD signals to send to the each wind turbine in each wind power plant is the same.
So the POD controller sends these additional requirements, active or reactive power.
Yeah.
Yes, and as I said, there are different configurations how you can do it. I don't know if your question is relating, if you decide when you are doing it, if it's active power or it's reactive power. I don't know if this is your question about modulating either active.
It's about active power. Yeah.
So active power, right?
Yeah.
For example, as I said, so the dispatch, the controller can send this requirements, these delta signals to each individual wind power plant based in a proportional, maybe proportional way, namely according with the size of wind power plants. I think that we have done it like this, if I remember it right. But of course, as I said, a more complex, detailed dispatchment can be done.
Because I have read some papers, and many papers only consider a graduate wind farm, and but in the application, we use every wind turbine to participate in the power oscillation damping. So we should send the POD signals to each wind turbine.
But this can be done, as I said, if you know an idea about the available power for each wind turbine, right? So the controller gets information about the estimated available power, and then if you choose this proportional dispatching, you can do it based on the size of the available power and the size of wind turbines. And send the references. If this is the question, I'm not sure that I understood it right. But okay, I thought first, because as I said, you can choose different control strategies, different inputs and outputs you can combine. But your question was related with the dispatching of active power for POD.
Just wonder whether your research group have any publications research about this, so that I can.
Yes, of course. If you can send me an email, I will send you. We have actually a report about our work on this POD. So I can send it to you. For sure. Please send me an email, and I will forward to you.
Okay. Thank you very much. I will send my email to you after this meeting. Okay. Thank you.
Thank you.
Thank you, Anca, and thank you, Juan. I see, Julia, you still have your hands raised. Is there a follow-up question? Or this is from the previous time?
It's from previous time. Sorry, I forgot to forward.
No worries. But thank you, all the presenters. Then I would not take your time further. We are already used more time than what we promised. But please remember, we have